Section 8.3, Multiply, Divide, and Simplify Radicals. From the last section, we saw that if we didn't have the same index, we would need to put them into rational exponents to continue. Well, in this section, we are going to have the same index. So to multiply and or divide radicals, you must have the same index. If both the nth root of a and the nth root of b are real numbers, then the nth root of a times the nth root of b equals the nth root of a times b. If both the nth root of a and the nth root of b are real numbers, then if you're dividing the nth root of a by the nth root of b, that's going to equal the nth root of a divided by b, where b cannot be 0. So all this is stating that is if you have the same index and they're separated, you can put them together, and vice versa. If they're together, then you can separate them into their own radical, keeping that same index. So my suggestion to you is whenever you look at a problem and you are separated, meaning multiple radicals, see if you can put them together. So for number 1, it says find the product and simplify. The square root of 3 times the square root of 12. The index is the same. The index is a 2, so we can put them underneath the same radical. So we end up with 3 times 12 underneath the square root, which gives us the square root of 36. And the square root of 36 is just 6. So in my face-to-face class, I'm always saying if they're separated, put them together. So looking at number 2, the square root of 8y to the third times the square root of 2y. They are separated, and because the index is the same, we can put them together. So 8 times 2 is 16, and when we're multiplying, we add powers, so we get y to the fourth underneath the square root. What's the square root of 16? It's 4. And we learned from the previous sections that when we have variables, we take the power and divide by the index. 2 can go into 4 2 times with the remainder of 0. So y squared is also going to come out, and nothing is left under the radical. Number 3, we have the cubed root of 3m times the cubed root of 2m. They are separated, meaning multiple radicals. Because they have the same index, let's put them underneath the same radical. 3 times 2 is 6, and when we multiply, we add powers, so we get m squared. There is not a nice cubed root of 6, and m squared does not have enough for its power to come out, so therefore you are done, and my answer is the cubed root of 6m squared. Simplify. Assume that variables represent positive values. Again, the reason why we need positive values is because if we have fractions, we don't want 0 in the denominator. So we're just going to make sure that we don't have negatives under our square roots and that our denominators don't become 0. So number 1, the square root of 18 over the square root of 81. They're separated. They're different radicals, but they have the same index. So let's put them underneath the same radical to see if we can reduce. So we get the square root of 18 over 81. Because they're underneath the same square root, we're allowed to reduce those. 18 over 81 reduces to 2 over 9. Now that that's all we can do underneath the radical, we'll re-separate them into the square root of 2 over the square root of 9, and the square root of 9 is just 3. So we end up with the square root of 2 over 3. Number 2, the square root of 15 over the square root of 5. Separated, there's nothing we can do, but if we put them together, we get the square root of 15 divided by 5. And 15 divided by 5 is 3, so we end up with the square root of 3. So keep asking yourself that question. If there's multiple radicals with the same index, put them underneath the same one to see if you can simplify. Now when we do that on number 3, we have the cubed root of 5a over the cubed root of 8r to the 6. If we put them underneath the same radical, the cubed root of 5a over 8r cubed, we see that we cannot reduce, nothing cancels. So if we re-separate them, we're back to where we started from, the cubed root of 5a over the cubed root of 8r to the 6. Now in the numerator, the cubed root of 5a, nothing can come out of that. However, in the denominator, there is a nice cubed root of 8, that is 2. And when we take power divided by index, 6 divided by 3 is 2, so we end up with an r squared on the outside. But most of the time, if they're separated, put them underneath the same radical to see if you can reduce. Simplify. Assume all variables represent non-negative values. So these problems below are going to be ones that not everything always comes out. So we're going to either need to do a factor tree or know our squares or our cubes really well. So number 1 says 3 times the square root of 245. That is not an index, that is on the outside. So 3 times the square root of 225, if we type 225 into our calculator and take the square root, it does not give us a nice value. So I suggest doing a factor tree. Because the index is a 2, we'll be looking for pairs. Well, how can I break up 245? Well, I know it's divisible by 5, and when I take my calculator, I'll notice that 5 times 49 is 245. 5's prime, so I'll underline it, but 49 is 7 times 7, and I'll underline those two. So I look for pairs because my index is a 2, and I have a pair of 7's. So that means the 7's going to come out, but there's already a 3 on the outside. So the 3 stays on the outside, a 7 comes on out, and a 5 is left underneath. So I end up with 21 times the square root of 5. So I like to do the factor tree. If you just want to find the perfect square, you can do that as well. So number 2. The square root of p to the 4th, q to the 8, r to the 6. Well, we have variables underneath the radical, so we just take power divided by index. When I take my power of p, which is 4, divided by 2, I see p squared comes out. When I take with my q, the power of 8 divided by 2 is 4, so q to the 4th comes out. And r to the 6, when I divide by 2, 6 divided by 2 is 3, and everything comes out of the radical, so no radical is left. For number 3, we have the cubed root of 54. Highlight the cubed root. Make sure you understand that it's a different index than a square root. So if I look at the factor tree of 54, I could say 54 is 9 times 6, and neither of those are prime. 9 is 3 times 3, so I'll underline those, and 6 is 3 times 2, so I'll underline those. Always underline the prime numbers. Now, I need a cubed root, which means I need to circle triplets. And here I have 3 3's, so I know that a 3 is going to come out. Don't forget your index of a 3, and a 2 is left underneath. The reason why a 3 comes out is because the triplet, 3 times 3 times 3 is 27, and the cubed root of 27 is back to 3. Number 4, we have the cubed root of 48h to the 14th. Be careful, this is a cubed root. First thing you want to do is a factor tree. The way that I see 48 breaking up is 6 times 8. There are other ways, but that's the way that I see it. So 6 is 3 times 2, those are prime. 8 is 2 and 4, 2's prime, but 4 is not, so 4 is 2 times 2. Because my index is a 3, I need to circle triplets, and I do see that I see 3 2's. So a 2's going to come out, and so far what's left is the 3 and the 2. So I re-multiply the 3 and the 2, and that gives me back a 6 under the radical. Now let's work with the variable. The variable had a power of 14, and I take 14 and divide by 3. How many times can 3 go into 14? It can go 4 times with the remainder of 2. We haven't worked with the remainder yet, so what does that mean? Well, the 4 still tells you in the power form how many h's come out, so h to the 4th. So the remainder tells you how many h's are left in power form, so h squared has to be left underneath. So my final answer is 2h to the 4th times the cubed root of 6h squared. Number 5, the 7th root of a to the 16th, b to the 9th, c to the 12th. Well, we don't have any numbers to deal with, but we do have lots of variables. So how do we start it off? We take the power divided by index. So 16 divided by 7, if we're going to work with the variable a. 7 can go into 16 2 times. 2 times 7 is 14 with a remainder of 2. So what does that mean? Well, that means 2 of the a's, a squared comes out, and with the remainder of a 2, a squared is left underneath. So a squared comes out, leave a little bit of space, and a squared stays underneath. Let's work with the b. b to the 9th, so the power is 9, and I divide by my index 7. 7 can go into 9 one time with the remainder of 2. So the whole number says how many b's come out, so b to the 1st. I have a remainder of 2, so b squared has to stay underneath. Now let's work with the c. What power did c have? It had a power of 12. So I take 12 and divide by my index 7. 7 can go to 12 one time with a remainder of 5. So again, c to the 1st comes out, and c to the 5th stays underneath. The 1's are understood to be there, so we'll rewrite that as a squared times b times c times the 7th root of a squared, b squared, c to the 5th. So the 1 is understood to be there, so you do not need to write them. Find the quotient and write in simplest form. Assume that variables represent positive values. Number 1, 10 times the square root of 280, all over 2 times the square root of 10. First question would be, can I reduce the 10 and the 2? And the answer is actually yes. And the reason why is because addition and subtraction stick things together like glue. But when you have all multiplication, you are allowed to cancel with multiplication. And this is 10 times the square root of 280 and 2 times the square root of 10. So you're definitely allowed to cancel the 10 and the 2. With the square root, they are having the same index, so we're going to put them underneath the same radical. Well, 2 can go into 10 5 times, so I know I'm going to have a 5 on the outside. Putting them underneath the same radical, I get the 280 divided by 10. So when I reduce 280 over 10, I get 5 times the square root of 28. Now I need to do the factor tree. 28 is 4 times 7, 7's prime. 4 is 2 and 2, and the 2 is now prime. I circle a pair because I'm looking for pairs, because my index is a 2. The 5 is going to be on the outside, a 2 comes out, and a 7 is going to be left. So my final answer is 10 square root of 7. Number 2, we have 6 times the square root of 48 into the 7th, all over 3 times the cubed root of 3 into the 3rd. Just like in the previous problem, we are allowed to cancel the 3 and the 6, so we'll get a 2 on top. And because we have the same index, we'll put them underneath the same radical to see if that helps. So we'll have 2 times the square root of 48 into the 7th, all over 3 into the 3rd. So underneath the same radical, are we allowed to reduce? Yes. 48 divided by 3 is 16, and when I'm dividing, I subtract powers, so 7 minus 3 is 4. So I have 2 times the square root of 16 into the 4th. Is there a nice square root of 16? Sure. The square root of 16 is 4, so the 2's already out there, a 4 comes out. I'll take my power of 4 and divide by my index of 2, so n squared comes out, and the remainder is 0, so none are left underneath. So my final answer is 8n squared. Number 3, the square root of 5y to the 3rd over 3 times the square root of 10y to the 6th over 27. Since we have multiple radicals and they have the same index, I'm going to put them underneath the same index. So we'll have the square root of, multiplying straight across, 5 times 10 is 50, and when I multiply, I add powers, so 3 plus 6 is 9. All over 3 times 27 is 81. Now that I put the stuff together, I look to see if I can reduce it all, and I cannot. So the next thing to do is reseparate them and then simplify each radical. So I get the square root of 50y to the 9th over the square root of 81. Well, I know what the square root of 81 is, that's 9, so I'll just have a 9 down in the denominator. But let's do the factor tree on the 50. 50 is 5 times 10, 5 is prime, 10 is 5 times 2, and now the 2 and the 5 are prime. I'll circle pairs because my index is a 2. So that means a 5 is going to come out. I'm going to leave a little bit of space, and the 2 is going to be left underneath. But now I have to work with the variable. So working with the variable, we have y to the 9th. I'll take my power of 9, and I'll divide by my index of a 2. So 2 can go into 9 4 times with the remainder of 1. So that means 4 comes out, and the 1 stays underneath in power form. So y to the 4th comes out, and y to the 1st stays underneath. I don't need to put to the first power because it's understood to be there. So I end up with 5y to the 4th, square root of 2y, all over 9. Find the product and simplify. 4 times the square root of 6c cubed times 3 times the square root of 10c to the 8th. Well, when we're multiplying and we have multiple radicals, let's put them underneath the same radical to see if that helps. Well, the 4 and the 3 are on the outside, so I can multiply those and get 12. Then I multiply the things underneath the radical. So 6 times 10 is 60, and when I'm multiplying, I add powers, so I get 8 plus 3, which is 11. So I get c to the 11th underneath the radical as well. Now I'll do the factor tree on the 60. I see 60 as 6 times 10, and 6 is 2 times 3, and those are prime, and 10 is 2 and 5, and those are prime. I'm looking for a pair, and I see that I have a pair of 2's. So 12 is already out there, times a 2 is going to come out. Let's leave a little bit of space because we'll work with a variable in a second. And underneath, what's still underneath the radical is the 3 and this 5. So 3 times 5 is 15. So 15 is still left under the radical. Now let's work with the variable. The variable was c to the 11th, so I take my power 11 and divide by my index 2. 2 can go in 11 5 times with the remainder of 1. So c to the 5th comes out and c stays underneath. So c to the 5th comes out and 1c is left underneath. So 12 times 2 is 24, c to the 5th, square root of 15, c is my final answer. Number 2. 6 times the square root of 15c cubed times 2 times the square root of 10c to the 4th. We'll start off by the same way. The 6 and the 2 get multiplied because they're on the outside, so I get a 12. And now I'll multiply the numbers and the variables underneath. So 15 times 10 is 150. And when I multiply, I add power, so 4 plus 3 is 7. I'll then do the factor tree. 150 is 15 times 10, and 15 is 5 times 3, and 10 is 5 times 2. So I'll look for a pair. And I see that I have a pair of 5s. So 12 is already out there, and a 5 is going to come out. Leave a little bit of space, so we'll work with the variable. What's left underneath the radical so far is this 3 times this 2. So 3 times 2 is back to 6. Now we'll work with our variable. Our power had a 7, and we divide by the index 2. 2 can go into 7 3 times with a remainder of 1. So we know that c to the 3rd is going to come out, and c to the 1st is going to stay underneath. So multiplying 12 times 5, I get 60. C to the 3rd, square root of 6c.